So if you just look down at your smartphone right now, or maybe look up at the monitor you're probably sitting in front of, you're looking at this sheet of, perfectly smooth glass, or maybe a sleek piece of brushed aluminum. And there's this really inherent psychological trick happening there.
Oh, absolutely. The design is intentionally deceptive.
Right. It's built to completely hide the orchestrated chaos that's happening just like millimeters beneath that surface. Because, we expect physical transparency in our lives. Like when you ride a bicycle, you press a pedal, the tension transfers to the chain, the gear catches.
You can actually see the physics happening.
Exactly. You can trace the mechanics. But with a computer, that transparency just vanishes. You're staring at this silent black box, and you're just expected to implicitly trust that inside it's somehow perfectly executing billions of microscopic electrical events every single second just to, render a video game or stream a movie.
It creates a huge cognitive dissonance. We rely on these devices more than anything else, yet most people operate with this almost magical understanding of how they work. The actual architecture is just completely abstracted away behind the user interface.
Which honestly is fine if you're just sending a text message. But it becomes a massive liability if you're the university student listening to us right now, staring down a high-stakes multiple-choice exam on computer fundamentals.
Yeah, that abstraction is your enemy on an exam.
Right, because you can't just memorize textbook definitions. If you don't know the why and the how, the examiners are going to trip you up with trick questions. So to you, the student grinding through the study guides, this deep dive is entirely for you.
We really want to give you that structural understanding.
Exactly. We've pulled apart the most authoritative computer science textbooks. We are not just going to read you a glossary. We're going to dismantle the computer, trace the electrical pathways, look at the memory hierarchy, and figure out how the physical world interfaces with the digital one.
And by the end of this, you won't just be guessing at those multiple choice answers. You'll actually be able to reverse engineer them.
So let's just jump right in. Let's start with the absolute foundation, because I know this is where the exam traps usually start.
Yeah, before we even touch on silicon or microchips, we have to define what a computer fundamentally is. So the root of the word, from Latin, computars, it literally means to calculate. But the modern academic definition is, an advanced electronic device designed to manipulate data according to a set of instructions.
Okay, but the danger there lies in a single word, right? Data.
Yes. Yes, the word data. Because in everyday conversation, we use data and information like they're exactly the same thing.
Right, like, hey, look at this data, or send me that information.
Exactly. But on a computer science exam, treating those as synonyms will instantly cost you points. They represent two entirely different states. Think of it in terms of entropy.
Entropy, okay.
Yeah. So data is raw, unsequenced facts and figures. It's high entropy. It has absolutely no context. If I just feed a computer the numbers 4, 12, 19, and 88, that is data. It means nothing to a human. Is it a date? Lottery numbers? The computer doesn't know, and it doesn't care.
Because the machine doesn't actually understand anything inherently.
Right. Its entire purpose is to lower that entropy. It applies logic to transform those chaotic numbers into something ordered. So maybe it applies a label, turning those numbers into, say, a list of daily temperatures. That resulting contextualized output is information.
Oh, I see. So it's kind of like baking a cake. The data is just the raw flour, the sugar, the egg sitting on the counter. It's not a cake yet.
That's a perfect analogy, actually.
And the processing is the mixing and baking. And then the information, the output, is the finished edible cake.
Exactly. Information is just data that has been processed and given meaning so a human can use it. And that brings us to the operational reality of literally every computing device ever built. The IPO cycle. Input, processing, output.
I really want to break down the physical reality of that cycle, though, because it's not just an acronym. Like, input isn't just typing on a keyboard. It's a physical translation of our world into binary, right?
Yeah, it's taking the analog reality.
Like the physical pressure of my finger on a key.
Right, or the sound waves of a voice.
Yeah.
And forcing it into a digital format the machine can handle. That raw material is fed in. Then processing is the microscopic shifting of electrons through logic gates to alter that code.
And output is the reverse translation, turning the binary back into light from a screen or sound from a speaker.
And from an exam strategy perspective, you really have to watch out here. The IPO cycle is often tested by examiners inserting a distractor step.
Like what?
Like they'll give you options such as input, storage, processing, output.
Uh,
Or they'll mix up the order. You have to remember the strict causal chain. You cannot process what hasn't been input, and you can't output what hasn't been processed.
though sometimes they do accept IPOS, right? With storage at the end?
Yeah, IPOS is sometimes used because the resulting information usually needs to be saved. But the core transformative engine is strictly IPO.
Okay, so if every computer runs that exact same IPO engine, it raises a huge question about how we classify them. Because, I mean, a digital thermometer and a massive server farm are both doing IPO, but they are clearly different things.
Right, and textbooks categorize computers in a few ways. The first major division is based on their fundamental operating principles. So we have analog, digital, and hybrid.
Let's start with analog, because we really have to discard the idea of binary code completely here, don't we?
We do. Analog computers don't count zeros and ones at all. They measure continuous physical variables, so voltage, fluid pressure, mechanical rotation.
So it's mapping a physical phenomenon directly to an output, like a classic mercury thermometer. As it gets hotter, the liquid continuously expands. There are, infinite fractional points between 20 degrees and 21 degrees, and the analog device represents all of them in this smooth, continuous sweep.
Exactly. It's a continuous wave. Analog computers are incredibly fast at solving specific equations because they don't pause to calculate, they just let the physics happen. But their fatal flaw is precision.
Because physical things get interfered with. A tiny change in room temperature or a bit of friction alters the analog signal.
Right, you lose absolute precision, which is why the industry shifted to digital computers. Digital abandons the continuous wave and forces everything into discrete states, on or off, 1 or 0.
It's the difference between a ramp and a staircase. An analog signal is a smooth ramp. A digital signal is a staircase. You're either on step 1 or step 2. There's no in between.
And that quantization eliminates the noise problem. If interference makes a voltage slightly weak, it doesn't matter. As long as it's above a certain threshold, the digital logic gate just reads it as a firm 1. It gives you absolute, repeatable precision.
Which is why everything from your laptop to internet servers are digital. But our physical world is still analog. Our heartbeats, the weather. So that requires the third category, right? Hybrid computers.
Yes, and this is exactly where exam questions like to focus. You'll almost always see hybrid computers tested using medical or industrial examples.
Like an ICU heart monitor.
Perfect example. The patient's heart rate is a continuous analog biological signal. The monitor uses analog sensors to capture that wave. But to store it in an electronic health record or trigger a digital alarm, that wave has to be digitized.
So the machine takes rapid snapshots of the analog wave, thousands of times a second, and assigns a binary number to each snapshot. It builds a digital staircase out of the analog ramp.
Exactly. Understanding that bridge is key. Okay, so that covers how they operate. Let's look at how we classify them by scale and capability, because textbook definitions can feel really outdated here.
Oh, for sure. We have microcomputers, mini-computers, mainframes, and supercomputers. A microcomputer is defined as a small, inexpensive machine using a microprocessor, like a smartphone. But wait, if my smartphone is more powerful than a 1980s mainframe, why is it still just a microcomputer?
It's a huge point of frustration for students. The nomenclature seems tied to physical size, but it's really about microarchitecture and intended workload. Your phone is a marvel, yes, but fundamentally, its CPU is consolidated onto a single microprocessor, and its architecture is designed for a single user performing personal tasks.
So it's not about raw horsepower compared to historical machines. It's about its current role. One brain, one user.
Exactly. The next step up, mini computers, which are basically mid-range servers, are built for multi-tenant environments. They support dozens of users at once.
But the real battleground on an MCQ exam is the distinction between mainframes and supercomputers. Because they both just sound like massive, ultra-powerful machines. How do you tell them apart on a test?
You have to look for specific keywords. They represent entirely different engineering philosophies. A mainframe is obsessed with throughput and massive input-output volume. Think of a major credit card network processing tens of thousands of tiny transactions every single second.
So the math itself is easy. It's just addition and subtraction. The difficulty is juggling millions of them without dropping one.
Exactly. Mainframes are the ultimate corporate multitaskers. But a supercomputer is actually terrible at handling millions of tiny transactions.
Really? But it's a supercomputer. Shouldn't it be faster at everything?
Not efficiently. A supercomputer's architecture is built for extreme, singular focus. It takes one unimaginably complex problem, like simulating a nuclear explosion or climate change, and throws thousands of processors at that single problem in parallel.
Okay, so the mainframe is like the Postal Service, efficiently routing millions of small envelopes everywhere. And the supercomputer is a heavy lift rocket, focusing an astronomical amount of energy to push one massive payload.
That is the exact mental model you need. If the exam question says banking transactions or large databases, you select mainframe. If it says weather forecasting or quantum mechanics, you pick supercomputer. Oh, and quick trivia. They often test the Param series of supercomputers from India and Seymour Cray, the American engineer who pioneered the industry.
Good to know. We also have classification by purpose, which is general purpose versus special purpose. I feel like this one is pretty intuitive. Like, my laptop is general purpose because I can run a web browser, then play a game.
Right, the hardware is agnostic, but a special purpose computer has its instructions hardwired for a single task, like the computer managing the anti-lock brakes in your car.
Right, you can't install a word processor on your car's brakes.
And you definitely wouldn't want to. It strips away everything unnecessary to ensure zero latency for its one critical job.
Okay, so whether it's the brakes in a car or a bank's mainframe, they all converge on the same fundamental command center. Let's look under the hood at the CPU, the central processing unit.
The modern CPU architecture we're tested on is derived from the von Neumann architecture from 1945. The defining feature and a massive exam point is the stored program concept. The data and the instructions are stored in the same memory space. The CPU just continually fetches and executes them.
And the textbooks divide the CPU into 3 subsystems. And I know students get these mixed up. We have the arithmetic logic unit, the control unit, and the registers. Let's isolate the arithmetic logic unit, or the ALU.
If the CPU is a factory, the ALU is the heavy machinery. It is the only part that actually performs operations on the data. It does exactly 2 things: arithmetic, like addition and subtraction.
And logic.
Right. Logical operations are comparative. It takes 2 pieces of data and asks, is A equal to B? Is X greater than Y? This is what allows a program to make decisions.
So the ALU is the muscle doing the crunching, but it needs direction, which is where the control unit, the CU, comes in.
And this is a huge trap for exams. Students see control unit and think it processes data because it sounds like the boss, but the control unit never touches the data itself. It does 0 math.
If it doesn't do math, what is it controlling?
It controls the electrical flow, it's the orchestrate conductor, it reads the software instructions, decodes them, and fires off control signals to the memory in the ALU, telling them exactly what to do and when.
That leaves the third component, the registers. We hear about RAM all the time, but registers seem to get ignored, even though they're so critical.
They are the absolute peak of the memory hierarchy. Registers are microscopic slivers of memory built directly into the CPU core itself. They are the fastest memory in the machine, but they're incredibly small, usually just 32 or 64 bits.
So they aren't for storing files. They're essentially the CPU's own hands. Like, if you're doing a math problem on a whiteboard, the registers are the numbers you're holding in your head at that exact millisecond. What specific registers do students need to know?
There are 3 heavy hitters. First is the accumulator. When the ALU performs a calculation, the intermediate results go to the accumulator before the next step.
Okay, that makes sense. It accumulates the totals.
Second is the instruction register, or IR. When the control unit fetches a piece of code, it needs a place to hold it while it decodes it. It holds it in the IR.
So the IR holds the, what are we doing right now?
Yes. And third is the program counter, or PC. This holds the exact memory address of the next instruction that needs to be fetched.
It's like a bookmark. It makes sure the CPU doesn't lose its place.
Exactly. And the interaction between these 3 things forms the machine cycle: fetch, decode, execute, store.
Let's run through that cycle. Step 1, fetch.
The control unit looks at the program counter. The PC says, next instruction is at address 104. The CU grabs that binary code from main memory and puts it in the instruction register.
Step 2, decode. The instruction is sitting in the register, but it's just raw binary.
Right. The instruction decoder inside the CU analyzes that binary. It translates it into a physical routing of logic gates, like, this means ADD register A to register B.
Step 3, execute. The muscle goes to work.
The CU fires signals to the ALU, configuring it for addition. The ALU performs the physical calculation.
And step 4, store.
The physical output is written back, maybe to the accumulator or out to main memory: fetch, decode, execute, store. A modern CPU repeats this exact cycle billions of times every second.
That scale is just. It's almost impossible to visualize. But let's ground it in the motherboard. We keep talking about the CPU reaching out to main memory. How do these electronic pulses physically travel?
Through a bus system. A bus is a parallel collection of microscopic copper traces etched into the motherboard designed to move data. Examiners test the three distinct types: the data bus, the address bus, and the control bus.
The data bus is self-explanatory, carries the actual payload.
Yeah, it's a bidirectional highway carrying raw data into the CPU and processed information back to memory.
But the data bus needs to know where it's going, which requires the address bus.
Right, the address bus is unidirectional. It only flows outward from the CPU, and this is important. The width of the address bus physically limits the maximum amount of memory the CPU can use.
Oh, so if an exam asks why an old 32-bit operating system can only use about 4 gigabytes of RAM, it's because a 32-bit address bus can literally only generate about 4 billion unique binary addresses. It just runs out of numbers.
That's exactly it. It's a physical limitation. And finally, the control bus, which is the nervous system. It carries the command signals from the control unit to all other components to prevent electrical collisions.
Okay, so the CPU is this ultra-fast engine, but it has almost zero internal storage. It needs a massive staging area for the operating system and the applications. This leads us to primary memory.
The memory hierarchy is all about managing compromises. We want memory that is infinitely fast, large, and cheap. But physics dictates you can only pick two.
Let's look at RAM, random access memory, the primary staging area. The most defining characteristic of RAM, and this is guaranteed to be tested, is its volatility.
Volatility means RAM requires continuous electrical power to maintain its data. The ones and zeros are actively held in place by voltage. If your laptop battery dies, every single bit of data in RAM evaporates instantly.
But the textbook forces students to differentiate between the two physical implementations of it. SRAM and VRAM, static and dynamic.
Yes, the MCQs will ruthlessly test this. Let's start with DRAM, dynamic RAM. This is your main system memory.
How does it physically store data?
It uses one tiny transistor and one microscopic capacitor per bit. A capacitor is basically a tiny bucket that holds electrical charge. Full bucket is a 1, empty is a 0.
That sounds super efficient. What's the catch?
The catch is physics. Capacitors leak. The moment you fill it, electrons start bleeding away. Within milliseconds, a 1 bleeds out and becomes a 0.
Wait, the memory just leaks out. How does the computer not just crash instantly?
The memory controller has to constantly combat the leakage. It systematically reads every single capacitor and rewrites the data back into it, topping off the buckets before they empty. This refresh cycle happens thousands of times a second. That's why it's called dynamic RAM.
That seems horribly inefficient. The CPU has to wait around for the RAM to refresh itself.
It does introduce latency, but because it only needs one transistor and one capacitor, you can pack billions of them onto a cheap chip.
Which brings us to SRAM, static RAM. If DRAM is the leaky bucket, what is SRAM?
SRAM abandons the capacitor completely. It uses a complex arrangement of transistors, usually 6 of them, wired into a feedback loop called a flip-flop circuit. Once voltage pushes it into a 1 state, the transistors constantly feed each other current to hold it.
So no leakage, no refreshing.
Exactly. It's blisteringly fast. But because it takes 6 transistors instead of 1, it's exponentially more expensive and physically larger.
You couldn't afford a standard laptop with 16 gigs of SRAM. So where do we actually use it?
We use it to build cache memory. Cache is the vital buffer zone between the CPU and the slower DRAM.
It's like a small, high-speed desk right next to the CPU. The CPU doesn't want to walk across the room to the filing cabinet, the DRAM, every time it needs a number. So it predicts what it needs and puts it in the SRAM cache.
Yes. The CPU checks the cache first. If it's there, that's a cache hit. If not, it's a cache miss. And it suffers a huge latency penalty waiting for the DRAM.
Okay, but if both of these lose their minds when the power turns off, we have a problem. When you turn a computer on, the RAM is empty. How does the CPU even know how to boot up?
It needs primary memory that retains data without power, and that is ROM, read-only memory.
ROM is fundamentally non-volatile. The instructions are essentially etched into the chip.
Historically, quite literally. The earliest were mask ROMs. The data was physically laid out in the integrated circuit traces during manufacturing. It could never be altered. When the CPU powers on, it looks at the ROM chip.
And what's on it?
The BIOS, the basic input-output system. It has the bare minimum firmware to wake up the hardware, run a power-on self-test, find the hard drive, and pull the operating system into RAM.
But mask ROM was too rigid. If there was a mistake, the chip was garbage. So they invented PROM. Programmable read-only memory.
Right, you could buy blank chips and program them with a PROM programmer.
But I understand this was a pretty violent physical process.
It really was. The chip had microscopic fuses. The programmer applied high voltage, literally blowing the physical fuses to create the permanent zeros and ones. So a PROM could only be written to exactly once.
Which is so wasteful. So then came EEPROM, erasable programmable read-only memory. But the erasing mechanism sounds like absolute science fiction.
It's one of the most bizarre eras of computing. EEPROM chips had a small, transparent quartz glass window on top. You could look directly down onto the silicon. To erase the data, you had to physically rip the chip out, put it in a specialized device, and blast that window with intense ultraviolet light for like 20 or 30 minutes.
Wait, really? UV light erased the data.
Yeah. The UV photons had enough kinetic energy to excite the trapped electrons, allowing them to literally jump over the insulating barrier and drain away, wiping the chip blank.
I can't even imagine IT departments dismantling servers to give their memory chips a suntan for a firmware update.
They hated it. It was slow and risky, which drove the creation of EEPROM, electrically erasable, programmable, read-only memory.
And this is where the terminology feels like a lie. If we can erase it and write to it electrically,
Right.
why do we still call it read-only memory?
It confuses students endlessly. It's a legacy naming convention that stuck because it defines the role of the memory, not its limitations. Modern EEPROM, which is flash memory, can be written to, but it's much slower than RAM.
And it causes damage, right?
Yes. Forcing electrons through the insulating layer causes microscopic physical damage every time you erase and rewrite it. Flash memory wears out. So we still call the BIOS chip ROM because its architectural intent is to be read constantly, but only written to or flash maybe once a year.
That perfectly clarifies it. Okay, so RAM is tiny in capacity. If we want to store 50 gigabytes of video files, we have to move to secondary storage.
Right. Secondary storage is the massive pantry down the hall. It is non-volatile for long-term persistence. But the CPU cannot interact with it directly. It cannot execute a program off a hard drive.
The memory controller has to copy the data from the slow storage into the fast RAM first.
Exactly. And understanding the different physical media used for secondary storage is critical. We have magnetic, optical, and solid state.
Let's start with the oldest, magnetic tape.
It operates by coating a flexible plastic strip with a ferromagnetic material. A write head physically aligns the magnetic domains to point one way for a 1 and the opposite for a 0.
It's basically a VHS tape, and that dictates its biggest limitation, the sequential access.
Yes, this is frequently tested. Tape is strictly sequential. If the computer requests file number 500, it cannot jump straight to it. The motors must literally fast-forward miles of tape over the read head, sequentially passing files 1 through 499 before reaching your data.
Which introduces unbearable latency, so why do textbooks even mention it?
Because in enterprise IT, sequential access is fine for what tape does best. Infinite scalability and the lowest cost per gigabyte. It's used for cold storage. Massive archival backups. If the exam asks for a storage medium suited for archival backups requiring only sequential access, the answer is always magnetic tape.
But for everyday use, you need random access. You need to jump around instantly. That brings us to the hard disk drive, the HDD.
Hard disks provide random access. Instead of a long tape, an HDD uses rigid, spinning platters made of glass or aluminum coated in magnetic material.
Like playing a vinyl record.
Similar, but a hard drive head never actually touches the platter.
Because if it touched at 7,200 RPM, it would physically shred the data, right?
Right, a head crash. The spinning creates a microscopic cushion of air, and the read head flies nanometers above the surface. This allows the arm to snap instantly to any location.
Exams love to test how data is mapped here. We need to define tracks, sectors, and cylinders.
Imagine the platter is a tree trunk. The concentric rings are the tracks, but a track holds too much data, so we slice the platter like a pizza. Those pie-shaped wedges are sectors. A sector is the smallest addressable block of data.
And cylinders.
A hard drive has multiple platters stacked on a spindle. A cylinder refers to the exact same track number across all the stacked platters vertically. It's faster to write vertically down a cylinder than to move the mechanical arm.
Before we move on, floppy disk drives. They're obsolete but still show up on tests. Just know the historical sizes 5.25-inch and 3.5-inch, and that a 3.5-inch floppy held a paltry 1.44 megabytes.
Yeah, it's just a good benchmark for data density history.
So that's magnetism. Next is optical storage, CD-ROMs, DVDs, Blu-ray. It abandons magnets for light.
Optical storage uses a laser beam. During manufacturing, a high-powered laser burns microscopic indentations called pits into a polycarbonate disc. The flat areas between them are lands.
How does that translate into binary?
When you play the disc, a low-powered laser shines on it. The flat lands reflect light straight back, but when the laser hits a pit, the light scatters. The optical drive detects these rapid changes as the disc spins and translates it into zeros and ones.
We see acronyms like CDR and CDRW. CDR is recordable. How does that work?
You buy it blank. It uses a layer of photosensitive organic dye. Your computer's laser heats the dye, causing a chemical reaction that permanently darkens it. The dark dye scatters the read laser just like a physical pit. Because it's permanent, it's a warm medium. Write once, read many.
And CDRW, rewritable.
CDRW uses a phase-change metal alloy. A high-power laser melts the alloy into a non-reflective pit, but a medium-power laser anneals the metal, forcing it to crystallize back into a reflective land. You are literally melting and freezing metal on a microscopic scale.
That is wild. Why did we move from CD to DVD to Blu-ray, though?
Yeah.
The physical disc is the same size.
It's the wavelength of the laser. A CD uses an infrared laser with a wide beam. A DVD uses a red laser with a shorter wavelength, focusing into a tighter spot so you can pack pits closer together. Blu-ray uses a blue-violet laser with an even shorter wavelength, allowing for microscopic data density for HD movies.
But both optical and hard drives have moving parts. Motors fail. This drives the industry to solid state.
Solid-state drives, USB flash drives, they eliminate mechanical movement entirely.
They use the same EEPROM flash memory technology as the BIOS chip.
Exactly. Data is stored by trapping electrons in floating gate transistors. No spinning platters, no seek times. They access data instantly, making them incredibly fast, silent, and durable.
They usually connect via USB, the Universal Serial Bus, which provides both data and power over one cable.
Right. But remember, flash memory degrades. It has a finite lifespan based on total terabytes written. So controllers use wear-leveling algorithms to distribute data evenly so no single sector burns out too quickly.
Okay, let's pull back. We've constructed the internal black box, CPU, RAM, SSD. But a computer perfectly executing logic inside a sealed box is useless. It has to interface with our physical reality. This brings us to peripheral devices, starting with input devices.
The core function of input is translation. It captures a physical, analog event, a keystroke, a spoken word, and digitizes into a binary signal.
The most ubiquitous is the keyboard. The QWERTY layout is fascinating because it was literally designed to be inefficient.
Yeah, in the 1870s, for mechanical typewriters, if a typist was too fast, the metal arms would jam. QWERTY separated the most common letter pairings to physically slow them down, and now the muscle memory is so entrenched we can't move away from it.
For exams, you need to know toggle keys, like caps lock, which toggle a software state, and modifier keys.
Right. Shift, Control, Alt. A modifier key generates no input on its own. It just modifies the binary signal of the next key you press.
Next, pointing devices. Navigating a GUI requires translating physical movement into XY coordinates. The original mechanical mice used a heavy rubber ball that physically turned internal wheels,
which constantly collected dirt. Modern optical mice are marvels. They don't just shine a light. They have a microscopic camera taking thousands of photographs of your desk every second. A processor compares the frames, detects how the desk texture has shifted, and calculates speed and direction instantly.
That's a staggering amount of processing just to move a cursor. What about trackballs?
Functionally, an upside-down mechanical mouse. The chassis is stationary, and you manipulate the ball with your thumb. Good for tight industrial spaces. We also have joysticks, which use sensors to measure the angle of deflection for continuous directional input.
But manual data entry is slow. The real efficiency comes from scanning devices, and examiners are ruthless here. You must know the distinctions between OCR, OMR, and MICR.
Let's start with OCR, optical character recognition. If you scan a page on a flatbed scanner, it's just a digital photograph, a grid of pixels. The computer doesn't know what it says.
You can't open it in Word and edit it.
Right. OCR is the software layer. It scans the pixel grid for patterns. It sees a vertical line connected to a curved loop and says, that geometry represents the letter P. It translates the image into editable text.
OCR reads shapes, but OMR, optical mark recognition, doesn't care about shapes.
OMR is binary detection. It looks for a mark in a highly specific location, like filling in a bubble on your multiple-choice exam with a pencil. The OMR machine shines a light at the exact coordinates of question 1, option A.
It measures the reflection.
Yes. A blank bubble reflects light strongly. The The graphite from your pencil absorbs and scatters it. The machine detects the drop in reflectivity and registers it as a selected answer.
OCR is shapes, OMR is light reflection. But the banking industry needed something even more secure, which leads to MICR, magnetic ink character recognition.
Students confuse OCR and MICR all the time. Look at the bottom of a physical bank check. Those weirdly shaped numbers are printed with ink containing microscopic iron oxide particles.
So they're actually magnetic.
Yes. The sorting machine magnetizes the ink, then a read head reads the physical magnetic waveform emitted by the ink. Each blocky font number generates a uniquely shaped magnetic wave.
Why not just use OCR?
Fraud prevention. If someone photocopies a check, an OCR scanner might read the plastic toner perfectly. But a MICR reader detects zero magnetic waveform from standard toner and instantly flags it as fraud.
That's a phenomenal distinction. We also digitize other senses with microphones, which are acoustic to electric transducers. A sound wave vibrates a diaphragm, inducing a varying electrical current.
We use barcode readers, bouncing a laser across a universal product code, measuring the timing of the varying widths of black bars and white spaces, and biometric sensors like fingerprint scanners.
Which don't take a picture, right?
Right. A capacitive scanner measures the microscopic electrical variations between the ridges of your skin touching the sensor and the valleys hovering just above it, mapping a topological signature.
Okay, so the CPU crunches all this input, and the IPO cycle demands an exit strategy. The digital information must be translated back to the physical world. Output devices.
Divided into soft copy and hard copy. Soft copy is ephemeral, vanishing when the power is cut. Monitors. We have to start with the old CRTs, the cathode ray tube.
The massive ones from the 90s.
A CRT is a massive vacuum tube. An electron gun in the back fires a high-voltage beam of electrons toward the front glass, which is coated with phosphor dots. When the beam hits a dot, it emits light. Magnetic coils rapidly sweep that beam across the screen line by line.
But they used immense electricity and were huge, so the industry adopted LCDs, liquid crystal displays, which work by selectively blocking light rather than generating it.
Exactly. There is a constant white backlight. In front of it is a sandwich of glass panels holding microscopic liquid crystal molecules. By default, they let light through polarizing filters.
How do you make a black pixel?
The computer applies a precise voltage to the molecules for that pixel. They physically untwist, which changes the polarization angle of the light. The light hits the front filter at the wrong angle and is completely blocked. It's like millions of microscopic window blinds opening and shutting.
Textbooks specifically mention TFT displays. Thin film transistor. How is that different?
It's active matrix control. Early LCDs were passive. They sent pulses down a grid of wires, causing voltage to bleed into adjacent pixels, making blurry images. TFT solves this by putting a microscopic transistor directly on the glass behind every single subpixel. It switches a pixel on or off instantly with absolute precision.
Now, for permanent output, we need hard copy. Printers. The broadest categorization is impact versus non-impact.
Impact printers use physical force, like a typewriter. The dot matrix printer.
The really loud ones.
Yeah. A print head has a column of tiny metal pins. Electromagnets fire the pins outward, physically smashing an ink-soaked ribbon against the paper to leave a tiny dot.
The resolution is terrible, they're slow. Why are they still heavily featured in the curriculum?
Because of the physics of physical striking force. If you need to print an invoice on carbonless multi-part forms where you write on the top sheet and pressure creates copies underneath, a laser printer is useless. It just gently melts toner on top. An impact printer violently strikes the page, activating the chemical transfer through all the layers. They are mechanically irreplaceable for logistics and banking.
That is a great piece of insight for the exam. But for general use, we use non-impact printers.
Inkjet.
And laser.
Inkjet is simple conceptually. The print head contains hundreds of tiny nozzles that forcefully eject microscopic droplets of liquid ink directly onto the paper. It mixes colors perfectly for photography.
But for a 500-page report, you use a laser printer. And it doesn't spray anything. It's an exercise in static electricity.
The heart of a laser printer is the photoreceptor drum, a metal cylinder that holds a static charge but loses it when exposed to light. First, a wire applies a uniform negative charge to the drum. Then, a laser beam rapidly stands across it, pulsing on and off, drawing your document.
So wherever the laser hits, it neutralizes the charge, creating an invisible electrostatic stencil.
Yes. Then the drum rolls past the toner. Toner is a microscopic dry plastic powder with a negative charge. It's repelled by the blank background, but jumps through the air to cling to the discharged areas where the laser drew the text.
Then the paper is fed in and given a stronger positive charge, so it rips the negatively charged toner right off the drum, but it's just loose powder resting on the page.
Which is why the final step is the fuser assembly. The paper passes between heavy rollers heated to 400 degrees. They literally melt the microscopic plastic toner particles, fusing them permanently into the paper fibers.
That's why the page is warm when it comes out. And the final output device isn't for text, but for technical design. The plotter.
Laser and inkjet printers are raster devices. They build an image out of disconnected dots. An architect printing a blueprint needs continuous mathematical provision, vector graphics.
And that's what a plotter does.
Right. A plotter is a robotic arm wielding a physical pen. It physically draws continuous, solid lines. Flatbed plotters move the pen over stationary paper, while drum plotters move the pen left and right while rolling the paper back and forth.
Wow. Let's just take a deep breath and look at the architecture we've laid out. We've completely demystified the black box. We understand raw data versus information, the IPO cycle. We dismantled the von Neumann CPU, the fetch, decode, execute cycle, the registers. We explored the memory hierarchy, the leaky capacitors of DRAM, the flip-flops of SRAM cache. We navigated hard drive tracks and optical pits, and we covered all the peripheral sensors and output physics.
You now possess a mechanistic blueprint. When you sit down for that exam, you aren't relying on fragile memorization. If they ask about SRAM, you understand the physics of the flip-flop circuit. You have the analytical framework to see through the distractors.
But before we sign off, I want to leave you with one final provocative thought. Throughout this whole deep dive, our premise has been anthropocentric. We assumed humanity sits at both ends of the IPO cycle. We type on the keyboard, we read the screen. The entire architecture was built as a tool serving human comprehension.
It is the defining paradigm of personal computing.
But that paradigm is collapsing. We are accelerating into the Internet of Things, the IoT ecosystem. We are embedding billions of sensors into smart grids, autonomous vehicles, agricultural systems.
An unfathomable volume of raw input.
And the shift is this. Computers are rapidly becoming the primary input and output devices for other computers. A moisture sensor in a field captures an analog reading, digitizes it, and sends it directly to a cloud mainframe. The mainframe processes it against a weather supercomputer algorithm. The mainframe then outputs a digital command directly to an automated irrigation valve. The valve opens. The IPO cycle completes flawlessly.
And at no point in that entire cycle did a human being press a key or read a screen.
Exactly. Humanity has been entirely bypassed. So the question I want you to wrestle with is this. If the definition of computing is turning raw data into information that possesses meaning, what happens to our relationship with technology when the machine no longer needs us to feed it data and no longer needs us to read its output? When the black boxes we build stop talking to us and start exclusively talking to each other?
It forces us to ask whether the system is still a tool or if it's evolving into an independent infrastructure where we are no longer the operators, but just the inhabitants.
A heavy thought to keep you company while you fill out those OMR bubbles. Thank you for joining us on this architectural deep dive.
Trust your logic, trust your understanding of the mechanics, and crush that exam.
We will see you on the next deep dive.